Hello and welcome, Physics 30s. Mr. T here. We're just finishing off page 124 on binding energy. We're in nuclear theory right now, first lesson. All right, the equivalent energy associated with the mass defect of the nucleus is called the binding energy of the nucleus. The binding energy represents the minimum energy that must be put into the nucleus in order to completely break it apart into its component protons and neutrons. It is also the energy released when the protons and neutrons come together to form an atom. It is equivalent to the ionization energy of an electron for an atom. For example, in the Bohr model of the hydrogen atom, it takes 13.6 electron volts of energy to raise the electron from ground state to n equals infinity, thus removing the electron from the atom. So 13.6 eV is the electron's binding energy. If a proton captures an electron to make a hydrogen atom, then energy is released as photon energy when the electron descends to ground state. In fact, it is this binding energy which keeps the atom stable. If the mass of the nucleons was equal to the mass of the nucleus, then it would immediately fall apart with no energy added at all. All right, let's try a few practice questions. Let's take a look at the first one here. We've got, for the following isotopes, determine a couple of things here. So the nuclear notation, the nuclear charge in coulombs, so a couple more, the number of neutrons, protons, and nucleons, the total mass of the constituent nucleons in kilograms. Okay, so four things. Let's do cadmium here, so 114. So what you want to do is you want to get your periodic table, and if you take your periodic table, what you do is you first of all find cadmium. So it'd be element number 48 right here. You can see 48 and CD standing for cadmium. All right, so in the question here, what you do is you want to put the notation together. So the notation here would be, because the nuclear notation generally has, right, for an element X, a generic X, you have A, which is the atomic mass, and Z, the atomic number. The A is the number of total mass of the nucleus, and Z is the number of protons. Okay, so for cadmium, we put CD, and we have 48 and 114. So 114 is the atomic mass, 48 the atomic number. So that'd be the first part. How about the nuclear charge? So for the nuclear charge, we'd have the following. 48 times 1.6 e negative 19. Just a second, just grabbing my calculator. 7.68 times 10 to the negative 18. Coulombs. The next part, number of neutrons. Number of neutrons is, well, the difference between the atomic mass, which is 114, and the atomic number. So 114, take away 48, we've got 66 neutrons. For the number of protons, we have 48. And the number of nucleons, that's going to be 114. The total mass of the constituent nucleons. Okay, so the mass would be 114 nucleons times 1.66 e negative 27, the mass of a nucleon. Atomic mass units is what it is. All right, approximately 1.89 e negative 25, or in this case here, probably 1.9 e negative 25 kilograms. Okay, this one might have been rounded too to maybe like 7.7 e negative 18 coulombs, just to give two significant digits. All right, let's try another question here. So let's take a look at question number 2. Notice I'm skipping part B from number 1. I know you can try that. How much mass in kilograms must be converted to generate 71 giga-electron volts of energy? Okay, so we know that the energy is given by mc squared showing this mass energy equivalence. We know the energy, we want to know the mass, and so we have c is a constant, speed of light, and so we're going to solve for m. That's going to be e over c squared. Get rid of the periodic table for a sec here. Okay, the energy, 71 GeV. Well, G is billion, so it's 10 to the 9. So we'd have times, we just put E9, and then we need to multiply by 1.60 E negative 19 joules for every electron volt. In other words, converting the top to joules, and then making sure we're squaring the speed of light. Okay, the calculation. (1.26 E negative 25 kilograms). Okay, so that allows you to do 1b and 2b. Try those ones out.